All right, so this video is going to be talking about related rates. And related rates is when you differentiate a function with respect to time. So I'll go ahead and zoom in. You're differentiating a function with respect to time. Another way to think of this is how variables relate to each other. As time goes on. The key to remember here is that we are going to be using implicit differentiation. And you need to highlight that or star that or whatever, just to make sure that you remember that, because that's very important. So it says find the rate y is changing in this equation when x equals 1 and dx dt equals 2. So that means that as time goes on, your y is changing and your x is changing in relationship to time passing. So we're going to say the derivative of y would just be 1, but in relationship to time we have to put dy dt. So that's the implicit differentiation part, is it doesn't matter what variable you're working with, you're always going to do the derivative of that variable in relationship to time. So derivative of y is 1, and then we're going to say dy dt. So this is the relationship between y, how y changes as t changes, equals 2x dx dt. So derivative of x squared is 2x, and then as x changes in relationship to time, and then that would be plus 0. And if we go ahead and plug in when x equals 1 and dx dt equals 2, then we're going to say dy dt equals 2 times 1, 2 times x, times 2, which is 4. So dy dt, as x is changing with relationship to time at a rate of 2, whatever the units are, then the rate that y is changing in relation to t at that same time is 4. Okay, so some helpful hints when you're approaching these related rate problems is to annotate the problem. I was told that annotate is an okay vocabulary word. So if you don't know what annotate means, it means like underline, highlight, whatever. Annotate the problem and draw a picture. So pick out the important pieces of information and draw a picture to give yourself a better understanding. You don't have to draw a picture 100% of the time. Sometimes you can't really draw a picture, but typically a picture is going to help you think through the problem and use your common sense. You're going to write down the given information and identify what you're trying to find. Next, you should find an equation or formula. And once you have that equation or formula, you're going to take the derivative. And this is where you have to remember that when you take the derivative, you're doing implicit differentiation. So I'm going to write implicit. That means that for each variable you see in the problem, whenever you take a derivative with that variable after it, you're going to tack on dx dt or dy dt or dv dt or dA dt. You're always going to add that little thing at the end. Next, we're going to plug in the given conditions. And we will solve for our unknown. And then last, we will write the answer with units as a complete sentence. I may not always require you to write a complete sentence, but it's definitely something you should be able to do just to make sure that you can take the answer you got and put it back in a context of the problem so that you know for sure you know what you were solving for and what you were talking about. Now, when you're doing a problem like this, it's okay to struggle. I would say that when I was learning calculus the first time, related rates problems really were hard for me. And it's totally fine to struggle. However, it is not okay to struggle and leave a problem blank. So if you come to me and say and ask for help and you say that you have no idea what is going on in the problem, I still need you to have underlined important information. I need you to have done your best to draw a picture, and I need you to have written the given information so that you could try to identify what you're trying to find. Those first two things you can do based on the problem. So maybe you don't get all the information written down and that's what you need help with, but I should never see a student come to me and say, I don't understand this problem, I can't do it, and have it be completely blank. Because every single one of you is capable of underlining some information that seems important. Every single one of you is capable of sketching a picture based on the common sense of how a problem works, or at least getting it started. So if the problem is blank, that just tells me you haven't tried it all. All right, so it says a pebble, a pebble, not a pebble, is dropped into a pond. The radius of the outer ripple is increasing at a rate of 1 foot per second. So you guys can see that when you drop something into water, it makes a circle. So we're going to be dealing with a circle here. The radius is increasing at a rate of 1 foot per second. When the radius is 4 feet, what is the rate the total area of the disturbed water is changing by? So I'm going to say the radius of the outer ripple is increasing. That tells us that they're giving us a rate of the radius, not just the actual measurement of the radius. They say that the radius itself is 4 feet, and they want to know the rate the total area is changing by. So we're talking about a circle here. That means that we know that the formula that we're working with is the area formula. So we've got pi r squared. We have some different variables. So we have the area of the water. We have the rate that the area is increasing, which would be dA dt. We have the radius of the ripple, which is 4. We have the rate that the radius is changing, which is 1 foot per second. So I'm going to go ahead and write down the information I have. And so I have dr dt is 1 foot per second. I have that r is 4 feet. And I have that I'm trying to solve for dA dt. That's the one thing that I don't know in the problem. Right? So I annotated the problem. I didn't need to draw a picture because it was there for me. I wrote the given information and identified what I was trying to find. That was the dA dt. I found an equation that makes sense with the problem, and so now I'm going to go ahead and take the derivative implicitly of that so that I can plug in my given information and solve. So I have area equals pi r squared. And so the derivative of A is 1 dA dt. And pi is just a coefficient, so I don't have to think about finding the area of that. But the derivative of pi r squared, I would take the 2, drop it to the front. So that's 2 pi r to the 1, and then times the derivative of r, which is dr dt. And what you'll notice when you recognize these formulas is that the derivative of the area formula gives us the circumference formula, right? So area is units squared. This would be units to the 1 power. So what we've learned about the derivatives and their relationship before, that's going to be holding true as we do these problems. So if you're looking at a volume formula and you take the derivative of it, it's going to give you the area formula for that same shape. And that's something that you'll consistently notice as you do these problems. So at this point, we're going to go ahead and plug in the information that we know. And I'm going to say the majority of the time when we plug in information that we know, we're going to plug the units in with the number because that helps us keep track of our units for the end of the problem. So r was 4 feet. dr dt was 1 foot per second. And so when we multiply all these numbers, we have 2 times pi times 4 times 1, which is 8 pi. And when we look at our units, we have feet times feet per second, so that gives us feet squared per second. So as the radius is increasing by 1 foot per second, and the radius of the outer ripple is exactly 4 feet, then the area is increasing by 8 pi feet squared per second. Or we could say that that's approximately 25.133 feet squared per second. All right, so the total area of the disturbed water is increasing by 25.133 feet squared per second when the outer ripple has a radius of 4 feet. Oh gosh, that didn't help at all. Goodness gracious. Look at my eraser. It's covered in purple ink. That's not helpful. All right, we're just going to leave it. Okay, next problem. Air is pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. Find the rate of change of the radius when r equals 2 feet. How is the surface area changing at the same time? So today, as we do the problems, we might have to Google some formulas so that we have them. Eventually, we'll have done enough of these problems that we'll kind of be able to anticipate which formulas we need, and we'll be familiar with them because we'll have worked with them for a couple days. So it says a spherical balloon. A sphere is like a 3D circle, and so I gave you guys a picture of a spherical balloon there. So the volume of a spherical balloon is 4/3 pi r cubed, and the surface area of a spherical balloon would be 4 pi r squared. So we'll go ahead and annotate the problem just so we know exactly what we have that's important. So air is pumped in at a rate of 4.5 feet cubed per minute. If air is being pumped in, then that's talking about volume. All right, and maybe I'll be more specific and say that's dV dt because that's a rate that the volume is changing by. Find the rate of change of the radius. That's what we're looking for when r equals 2 feet. And then there's a second question, how is the surface area changing at that same time? So we're going to have, this is like a 2-part problem. The first part of the problem is going to deal with the volume. The second part of the problem is going to deal with the surface area. So we wrote our 2 formulas down. We can go ahead and write down the information that we have. So we have dV dt is 4.5 feet cubed per minute. We have that dr dt is something we want to solve for. We have that the radius is 2 feet. And we have that the rate of change of the surface area is something that we want to solve for. All right, so if I look at the information, sorry, excuse me. If I look at the information I have, you can see that these rates of change in this variable all work with the first equation, and that when we look at the second equation, derivative of SA and then derivative of R would be 2 unknowns in the problem. And so we're going to start off just by dealing with volume. So we're at the place in our problem where we should be taking the formula that we have and doing the derivative of that. So the derivative of V would be 1 dV dt. And the 4/3 pi is a coefficient for R, so I'm just going to take the 3 and multiply it in the front. 3 times 4/3 pi r squared dr dt. So I'm making sure to take the derivative implicitly. The 3's cancel, and I just get 4 pi r squared. And remember what I told you guys is that since volume, the derivative of volume would be surface area, you guys can see it matches, the formulas match, which is kind of interesting. All right, so we can go ahead and start plugging things in. We have dv dt is 4.5 feet cubed per minute equals 4 pi times, the r value is 2 feet squared times dr dt. So I've plugged everything in. I'm going to go ahead and just clean up the problem a little bit. So 8 pi times 2 squared is 4. So 4, did I say 8 pi? I meant 4 pi. 4 pi times 2 squared is 4. So 4 pi times 4 is 16 pi. And then we had feet squared, so that's feet squared, dr dt. And dr dt is what we're solving for, so I need to go ahead and divide each side by 16 pi feet squared. And so I get that dr dt is 4.5 over 16 pi. And if I think about my units, the feet squared on the bottom are going to cancel with feet squared on the top, and it's just going to leave feet per minute. And that rate of change makes sense for the radius. So feet per minute, the radius should be changing by units that are linear, and so that's what it's doing. So I'll go ahead and plug this in my calculator just to get an answer that makes a little bit more sense for the problem. And I get 0.090 feet per minute. Right, and then from there I can go ahead, because now I know that dr dt is 0.090. I'm actually not going to use 0.090, I'm going to use that exact answer. Feet per minute. And so now I can go back and look at the rate of change of the surface area with respect to time. So here, the derivative of SA, that's not a product rule. SA is representing one value. So I'm going to say derivative of SA is 1 times dSA dt. And the derivative of 4 pi r squared would be take the 2 and multiply it in front. So 8 pi r to the first times dr dt. And so I have that this is what I'm solving for right now. And so that equals 8 pi times 2 feet times 4.5 over 16 pi feet per minute. All right, so this pi cancels with that pi. 8 times 2 is 16, so this 16 is going to cancel with that 16. And so the surface area is changing at a rate of 4.5 feet times feet, so feet squared per minute. That is a coincidence that that number is the same as the change of the volume. That's not going to be the case every single time. Okay, so at this point we would write our sentence. So the sentence would be when the radius of the balloon is 2 feet, the radius of the balloon is increasing by 0.090 feet per minute, and the surface area is increasing by 4.5 feet squared per minute. I'll go ahead and write that. Okay, I'm going to go ahead and do one more problem so that these problems can sink in overnight. We can finish them in class. So this one says an airplane is flying on a path that will go directly over a radar tracking system. So here's the plane, here's the radar tracking system. If the distance between the radar tracking system and the airplane, that's called S, so here's the distance between them, is decreasing at a rate of 400 miles per hour when S equals 10 miles, what is the speed of the plane? So they didn't say it in the problem, but they showed you in the picture that the plane is flying at an altitude of 6 miles. So that's important to know. So if we think about this particular picture and what formula or equation would go with it, that would be looking at a right triangle. And so we're going to say that that's a squared plus b squared equals c squared, or in this case we have an x. So x squared, we can call this y since it's going up and down. X squared plus y squared equals s squared. And then we'll go ahead and write down some of the information that we have. So we have ds dt is decreasing, so it's negative 400 miles per hour. I'm going to write miles per hour like that so that when I use it in the equation I can think about my units canceling or whatever. If you wrote mph, that's not wrong. I know that s equals 10 miles. I know that y equals 6 miles. And then there's a little bit more that I have to think about in the relationship of the problem just to make sure that I know exactly what I'm doing. So what speed is the plane? That's going to be dx dt. That's the plane flying, the plane's rate of change or the rate of change of that side. So dx dt, I don't know. The rate of change of y is going to be nothing because this is a constant. The plane is going to stay at a constant altitude, so we're going to say dy dt equals 0. So anytime you have something that's going to be plugged in for a variable, but that number is not going to change, that rate of change would be 0. And so now we just have to think about, we have the s value, we have the y value at these specific moments in time. We can go ahead and use x squared plus y squared equals s squared to find that x value. So that means that in the problem we have all the numbers except for the question mark, because when you're solving an equation you can only solve for one thing at a time, which means that you must have the information for everything else. So I'm going to go ahead and write down how to solve for the x. So I'm going to say x squared plus 6 squared equals 10 squared. So we're just trying to figure out what x is at that exact moment where the altitude happens to be 6 and the distance is 10. So x squared plus 36 equals 100. That means x squared is 64, which means at that moment in time x is 8. So we're going to say x is 8 miles. Okay, so we have all the important information, we have a picture, we have a formula. Let's go ahead and take the derivative of our formula. So the derivative of x squared would be 2x dx dt, plus derivative of y squared would be 2y dy dt, equals the derivative of s squared, which is 2s ds dt. So now we just have a lot of numbers to plug in. I have 2 times 8 miles dx dt plus 2 times 6 miles times 0 equals 2 times 10 miles times negative 400 miles per hour. Okay, so I can go ahead and clean up this problem a little bit. This is going to zero out because it's 12 times 0. So what I have is I've got 16 miles dx dt equals 20 times negative 400. So 2 times 4 is negative 8. 2 zeros and a 0 makes 3 zeros. So negative 8,000. The units would be miles squared per hour. And then we're going to go ahead and solve for dx dt. So I'm going to divide by 16, divide by 16. And so dx dt, and that was miles, 16 miles. That means that dx dt is negative 500 miles per hour. And so the reason that this value is negative is not because the plane is flying backwards or anything. It's just negative because it's closing the distance. And that's why it's written as a negative. So we're not going to call it a negative. We're not going to say it's decreasing speed. We're just going to say, like, this is a velocity, essentially. And so velocity is telling us that we're flying in the negative direction because we're getting closer to something. So we're going to say when the distance between the tracking system and the plane is 10 miles, the plane is flying at 500 miles per hour.